Okay, another mechanism. Here we have an epoxide. We're taking it to a carbonyl. Doesn't do anything to the tips, right? That doesn't go anywhere. We see an inversion of stereochemistry at our methyl group, though. That should give us a clue about what's going on, or we need to at least explain it, right? Would be another way of saying that. All right. So what else do we have? Well, we've got our buddy BF3. Now, whenever you guys see BF3, right, this is a Lewis acid. Okay. Just like AlCl3, right? Um, it's a Lewis acid. Also FeCl3, right? You know, all these things are Lewis acids. And how do Lewis acids behave? Well, Lewis acids behave like acids, right? Lewis acids are deficient of electrons, right? They've got an open orbital, might be another way of saying it. So the first thing that's going to happen is we're going to make a Lewis acid adduct, right? Which just means that epoxide oxygen is going to bind to the Lewis acid, right? So you can think of it, right? You can think of it very similar to how you're just using H plus, right, under acidic conditions, right? You would protonate that epoxide, right? But we've got a Lewis acid here, right? No aqueous conditions, right? All right. So what is going to happen in this case? Well, we caused a problem, and the problem we caused is we now have a positive charge on that oxygen. Well, what would be the easiest thing to do to get rid of that positive charge? Well, we just break our, the easiest thing to do would just be to break that bond, right? But that's just equilibrium. That's just going us back to where to begin from. So let's break another bond. Let me back up here for just a second. So if we want to break another bond, we have two options. Break that bond there or break that bond there, right? Let's analyze both, right? Let's analyze both. I'll come back and fill in the colors in just a second here. Okay. If I follow the green pathway, I am left with this. If I follow the red pathway, I'm left with this, right? Oh my goodness. Okay. So follow your arrows, right? If I follow the green pathway versus the red pathway, one of those is better than the other, right? One of those is better than the other. And the question should be, well, which one is it? Hopefully at this point, right? Hopefully at this point in our organic careers, we can identify that purple carbon there as a secondary carbocation, and that yellow one is the purple one's tertiary, the yellow one's secondary. So which one's going to be better? Remember with epoxides, they're playing this game of sumo, right? They're going to open up to leave behind a positive charge at the most stable carbon, right? And hopefully you guys will see at this point that that positive at the purple carbon there, at the tertiary position, is going to be more stable, right? So this isn't on our plate here, right? This is not going to happen. So let's get rid of red, right? Well, now what? Well, we're going to do a shift here, right? What's going to happen is this hydrogen here is going to do a hydride shift over to that right there. And what is that going to cause? It's going to cause our CH3 to invert, right? Because the hydrogen's coming in dashed, right? Hydrogen's coming in dashed. Oxygen to BF3. That should have a negative charge with it still here. And now our positive charge is right there. Now why Why would that that carbocation shift happen? Well, we can stabilize, right? We can stabilize this with a resonance structure, right? We can stabilize this with a resonance structure. And that's what pretty much happens, right? This falls down while this breaks off, right? Keep forgetting my tips. All right, there's that. Here, O, double bond, O tips. There it is, okay? And my BF3 is out there. Not too bad, right? The key is Lewis acid, and then find the best cation, do a hydride shift, and then slam down a pi bond to make a carbonyl. Okay? And there we go. That's the end of exam 3.